For the transformation number 2, we want to make sure we understand the concept of having some real number out here in the front. We haven't talked about that yet, so don't worry about that. But the h and the k. So the h and the k, those are your money values, and you've just got to know that your vertex of the absolute value function will always occur at hk. And so identifying what the h and the k are would determine where that vertex is. And notice here that h is always being subtracted from x. And so in the first problem there, 2 is the h because 2 is being subtracted from the x. So then over here, when we see a number being added to the x, you have to understand that what's being subtracted from the x is actually a -4. If it's x plus 4, the -4 is being subtracted, because when you subtract the negative, really that ultimately means you're adding. So anyway, h has a value of -4, and k has a value here of whatever's added is your k, and here we have -3 being added. So it's like plus a -3. So k you have to identify as -3, h is -4. So that means the vertex, therefore, is -4, -3. So we go 1, 2, 3, 4, 1, 2, 3, and we have our vertex. The original function, the parent function without any transformations, looks like that. Absolute value is always a v, and so if we want to sketch the graph of that transformation, when we just move the vertex to the left 4 and down 3, and then we just draw the graph the same exact way. And that's it. So that's how you draw the graph. And then what we talked about is the, domain and range. We know that the domain is always all real numbers, because you can take the absolute value of any real number and add a number to that and subtract a number from that. So the range, on the other hand, if we label the vertex, we know again that the vertex is at -4, -3. The range, keep in mind, is always the lowest member of the vertex is going to contain the lowest member of the range. So the vertex is -4, -3, so therefore the lowest y value is -3. The highest y value, there is none, so we say infinity, because this does go on forever. Increasing, and again we use green and red, so the red would be for the intervals in which the function is decreasing, and it's decreasing until you get to that x value, and then increasing to the right of that. So the function is increasing from this x value of -4 all the way to infinity, and the function's y values are getting lower from -infinity all the way to -4. No horizontal asymptotes, no vertical asymptotes. The x-intercept, we always want to make sure we solve for x when we let y equal 0. So to find the x-intercept, we're going to let y equal 0, and we get the absolute value of x plus 4 minus 3. Tune into this here, because this is a good review from what we started off the year doing. Adding 3 to both sides, we get the absolute value of x plus 4 is equal to 3. What does that mean? It means that x plus 4 is 3 units away from 0. We can see there's 2 x-intercepts. So x plus 4 is either equal to -3 or x plus 4 is equal to +3. And when we subtract 4 from both sides, we get -7. Subtracting 4 from both sides over here, we get -1. So we see we have 2 x-intercepts. One's at -7, 0, and the other is at -1, 0. Now the y-intercept, we just let x equal 0. We can visualize that, but if we let y equal 0, we let x equal 0 to find the y-intercept, it gets confusing sometimes. We write y equals 0 plus 4 in the absolute value bar, so it's 0 plus 4 is 4, minus 3, 4 minus 3 is 1. So even though I drew the graph above 1, it's still what it shows here is that the y-intercept is 1, and we would indicate that by using coordinates 0, 1. There is no maximum value, but we do have a minimum value, and the minimum value is the lowest member of the range. And if we notice, we have a -3 as the lowest member of the range. Again, absolute value functions are not one-to-one. We NA on the slope. Vertex, we already said, was at -4, -3. And the axis of symmetry is always going to be x equals the x value of the vertex, and that's x equals -4.